You are welcome, students and viewers. In this video, we are going to consider Maths 105, differential and integral calculus. Remember, in our last video, we are discussing about function, and in function, we are talking about the limit of a function. Maths 105. Of course, today is 12. 11/2025. Okay, and in this lecture we're looking at differential and integral calculus. We are talking about limit of functions. Recall in our last video, we defined a limit of a function based on the epsilon delta definition. Epsilon delta, this one, epsilon delta definition. What have we said then? We said that let f be a real valued function and x naught be a real number, we say that the function f of x has a limit at x naught, has a limit, say L, at x naught, x tends to x naught, or at x naught, if so we write it like this: limit, this is how we write it, limit x tends to x naught, f of x is equal to L. And this is true if we have if for every epsilon, that is for all epsilon greater than 0, we have some delta, there exists a positive delta such that f of x, the absolute value of f of x minus the limit, is less than epsilon. Yeah, let me write epsilon like this, as I have started. It's less than epsilon whenever x minus x naught is less than delta. So this is the epsilon delta definition. And for it, you have to look at the Cartesian coordinate system. That's the graph of the function f of x. Here we have x naught, and here is x naught minus delta. Here is x naught plus delta, meaning that the distance here is what we know as the delta. Similarly here. So, and we have, this is, here is the limit, and here is the limit from limit plus some distance epsilon. Here is the limit minus some distance epsilon, meaning that from here to here is what we have as the epsilon, and also from here to here is the epsilon. So now if we plot some graph, so that if we we have something like this, okay, and this is the graph of the function f of x. So this is f of x. So you see the delta we are referring to is a very small distance, meaning it's a very small real number, and the epsilon is a very small real number. You see, is the distance between this epsilon plus L plus epsilon and L, and it's also the same distance here. Likewise, this is the same distance delta here and the same distance for delta here, so that the limit will exist at L whenever you can find a small value delta, no matter how little it is, so that f of x minus the limit is smaller than this distance, which is the epsilon, and it's a real number, as I told you. And so we have taken just a simple example on that, because this is 100 level course. We believe in the next level we are going to treat this in math 203 properly. So in today's definition, in today's lecture, we will consider the limit of the left hand limit, left hand limit. We are also considering the right hand limit, and then we consider the two-sided limits. So to define that, we say, okay, let f of x be a real valued function. Remember, we are considering function of one variable, that is x, a real valued function, and x naught be a real number, we say that the function f of x has a limit to the left, has a limit L to the left of f of x, to the left of x naught, that is values less than x naught, has a limit to the left of x naught L if we have for every epsilon, that's for all epsilon, let me write epsilon like this, greater than 0, there exists a positive delta, that's a positive distance, this one, for every small value of epsilon. Remember, epsilon is always the distance on the side of the limit, and delta is a very small distance on the side of the real number, namely the values of x, and the distance, this is measuring how far is this point from the limit, from x naught, and this is measuring the closeness of this point to x naught. And while this epsilon is measuring the closeness of this point to the limit. All right. Whenever this is given, we can always find a positive distance or positive real number x naught such that the absolute value of f of x minus the limit is less than epsilon whenever you have x naught minus delta is less than x, and this is less than x naught. So this is limit to the left. This value is to the left of x naught, as you can see. Okay, so let's take example. Example 1. So let's look at example 1. The first example we have is let f of x be equal to x square. This is a piecewise function. So it is equal to x square if x is less than 2. And this is equals to 3x if x is greater than or equal to 2. To find, we are to find limit to the left. That is limit to the left of f of x. Sorry, you should know that if this happens and you have a limit to the left of L, so the limit is written as f of x. So we write it as limit as x tends to x naught. We write this negative on the x naught to show that we are talking about limit to the left. That is, we are talking about all the values to the left of, or all the values less than x naught. So this is f of x is equal to L. This is whenever this definition is satisfied. So we say the limit, the left-hand limit exists, and it is equals to L whenever this is satisfied. So you should find the limit as x tends to x naught, x tends to 2 to the left. So we say solution, we have to solve. So you remember that f of x is equals to x square if x is less than 2. And this is 3x if x is greater than or equal to 2. So this is a piecewise function. It defines several values on the domain of f of x. So it is x squared if x is smaller than 2. It is 3x if x is greater than or equal to 2. Meaning, the left-hand limit is considering values, remember, less than x naught. And our x naught here is 2. So any value less than 2, this is where we are concentrating. Not here, because these ones are greater than 2, and we are considering values less than 2. So that limit f of x tends to 2 to the left, this is equal to, so you apply 2 here, this is x squared, so you have this is equals to 2 square, but this is equals to what? Sorry, so we have to say, okay, this is limit x tends to 2 to the left of what? X squared, because that is the function we are considering. That is part of the function we are considering, because we are considering the values of x less than or equal to 2, so we cannot consider this one. So this is equal to what? You just substitute x equal to 2 because it's a polynomial function. You just go direct. This is 2 square, and the answer is what? 4. So therefore, you have evaluated this limit, and the limit is what? So meaning the limit of f of x as x tends to 2 to the left of 2, this is equal to 4. So we move to the second example. Okay. We are still on the left-hand limit. Example 2. In example 2, we say, okay, let f of x, this is also a piecewise function, let f of x, so not a piecewise function this time around, let's take 3x plus 2. We are asked to find the limit of f of x as x tends to 1 to the left of 1. Okay, this is what we're asked to find. So the solution. So we have f of x to be given as 3x plus 2. Now, limit of f of x as x tends to 1 to the left, this is equals to the limit as x tends to 1 to the left of this is 3x plus 2, and that is equals to what? When you substitute, you put x equal to 1, this is 3 times 1 plus 2, and this is equals to 5. So that you conclude, therefore, the limit as x tends to 1 to the left of 1, this is equals to this is equal to 5. So you have found the limit to the left. That is the limit to the left of that function. So we now take example 3, where in this case we are considering a piecewise function. So we say, okay, let f of x to be equal to 5 if x is less than 0 and it is equals to x plus 1 if x is greater than or equal to 0. X is greater than or equal to 0. We are asked to find f of x to the left of 0. Find limit x left of 0 f of x. So write solution. So here we are going to consider the values less than 0, because that is the value, that is the function we are looking at. That is the part of the function. So we say that since this is the value of f of x, so the limit f of x as x tends to 0 to the left of 0, this is equal to what? Directly 5. And that is all. That is the answer. There is no substitution. It's already 5. So you just take the value and keep. And that is the answer. So this is example 3. So we have example 4. Okay, do we have example 4? Okay, we don't have example 4. All right. So the right hand limit now. Right hand limit. So we say let f of x be a real valued function and x naught be a real number. We have a real number. We say that f of x has a limit L to the right of x naught, that is values of x less than x naught. So as x tends to x naught, if and the limit, it has a limit, this which exists if for all epsilon greater than 0, there exists a value delta, there exists a delta which is also positive, such that the absolute value of f of x minus the limit L is less than epsilon whenever x naught is less than x naught plus delta. So we are talking of limit to the right here. So limit to the right. So and we write limit x tends to x naught to the right with a positive here to the left, with negative here to the right with positive, of f of x is equal to L whenever this condition is satisfied. So an example 1 in terms of the right hand limit. So or example 4 entirely. So let f of x be equal to x squared. So we should determine the value of the limit x tends to 2 to the right of f of x. So solution What is our f of x? Recall that f of x is x squared. And so the limit as x tends to 2 to the right of f of x, this is equal to the limit x tends to 2, right, of f of x. This is x squared. And this is equal to what? This is a polynomial function, so we put x is equal to 2. So we have x, so x is equal to 2, so you have 2 squared, and that is equals to 4. And so limit as x tends to 2 to the right of f of x is equal to 4. So that is the limit. Somebody may ask, we have a limit to the left, we have a limit to the right. Do they coincide? Yes, they do coincide. For example, here, if you say limit as x tends to 2 to the left of f of x, this is the same thing as the limit of x squared as x tends to 2 to the left, and this is equals to the square of 2, and that is equals to 4. So you see that the limit to the left is equal to the limit to the right. And in general, when a function, if you have a polynomial function, so the limit to the left is equals to the limit to the right, and that is the actual limit of that function. Okay. So let's look at this example. So this example is, okay, the previous example. So example number 2. In this situation, I will bring that the previous example. So let f of x be equals to the piecewise function 5 if x is less than 0, x plus 1 if x is greater than or equal to 0. So let's find limit. Okay, find limit to the right of 0 of f of x. So we now say, okay, limit to the right of 0 of f of x is equal to, because we are saying limit to the right, so we are taking the positive values, the positive values after x, or the values after the value of our x, above x, I mean. Okay, so that is meaning we are taking this side. So we have, this is limit x tends to 0 to the right of what? X plus 1. And this is equals to what? So if we put x equal to 0, because this is a polynomial function, clearly we have what? So 0 plus 1, and the answer is equal to 1. So remember that in our limit to the left, but limit to the left of 0 is of f of x, if you can remember, is just equal to 5 here. So you see, the two limits now differ. We are coming to a definition that will take care of that. So that is to say, a function f of x can have one-sided limits different from the other. You know, this limit to the right, or the right-hand limit, and the left-hand limits are both called the one-sided limits. So now we are going to consider the two-sided limits, and that is the true existence of limit of a function. So the limit of a real valued function exists at, say, a real number x naught if the left hand limit is equals to, or let me just write limit x tends to x naught to the left of f of x is equals to the limit to as xx to x naught to the right of f of x. So if the two limits are equal, then we say that the limit exists. Otherwise, the limit does not exist. Let's take this example as example 2 as our example 1 here. Example 1. So let f of x to be equals to 5 if x is less than 0 and x plus 1, otherwise, that is if x is greater than or equal to 0. So we want to see whether the limit exists. So we are asking, does the limit of f of x exist at what? At 0? Meaning, what we mean here is, do we have a limit for as x tends to 0? That is the two-sided limit, the one we have defined in our first lecture. Okay? So what is the limit now? Does it exist? So I don't have to clean, just write f of x. Because, so you look at it, limit to the left is equal to 5, and limit to the right is equal to 1. So you see that the limit x tends to 0 to the left of f of x is not equal to limit to the right of f of x. Limit f of x as x tends to 0 to the right. So the two limits are not the same. And therefore, we conclude here that the limit f of x as x tends to 0 does not exist. Exists. That's all. The limit does not exist. So the limit will exist if and only if the two-sided limits are equal. That is, the left-hand limit is equal to the right-hand limit. We have, okay, let's look at another example. We are still on existence of limits. Okay. All right, let's take example 2. Let f of x. So in this example, we're saying let f of x be equals to x squared plus 1. We are asked to find limit of f of x as x tends to 3. That is we are to find the limit. So for us to find the limit, we have to find the left-hand limit and the right-hand limit, meaning we should find the two-sided limit of that function. Scene is pouring. Okay. All right. So the solution there is so we see that f of x is equal to x squared plus 1. So limit, we start with limit to the left. X tends to 3 to the left of f of x. This is equals to the limit x tends to 3 to the left of x squared plus 1. And that is equals to what? 3 squared plus 1. And that is equals to 3 squared is 9 plus 1, 10. So, okay. So now we should also find the limit x tends to 3 from the right of f of x. And this is equals to the limit x tends to 3 from the right of x squared plus 1. And that is equals to 3 squared plus 1. And that is also equal to 10. So we see that the left-hand limit is equals to the right-hand limit at 3. And therefore, we conclude that the limit as x tends to 3 of f of x, which is equals to that, is equals to 3. Is equal to 10. The limit exists and it's equal to 10. Okay. So let's look at another interesting example. So example 3, under existence of limit. So let f of x be equal to the absolute value of x minus 2 over x minus 2. Find the limit. We are asked to find limit of f of x as x tends to 2. As x tends to 2. Okay, for us to find the limit as x tends to 2, we should find the left-hand limit at 2, then we should find also the right-hand limit at 2. If the two limits coincide, definitely the limit exists and it's equals to that unique limit we have determined. So to solve this solution, so that is what? So we have f of x is equal to absolute value of x minus 2 over x minus 2. So now the limit x tends to, we should start with the left-hand limit here. So at x tends to 2, f of x this is equal to. But clearly here, to the left, here, we are taking the values less than the content of the absolute value. So meaning, at the negative, when x is less than 2, we have this function to be, so we write the limit at x tends to 2 to the left, and this is what? This is minus x minus 2. That is to the left over x minus 2. That is to the left of this value. And so this is equals to limit x tends to 2 to the left, and this is equals to minus, so this is equal, this is, yeah, this is it, without the absolute value, please. So this is minus 1 into x minus 2 over x minus 2. So the x minus 2 up and down will cancel, and what you have is that the limit x tends to left of 2, this is equals to minus 1. So the left hand limit is minus 1. So let's look at the right hand limit. Okay. So limit x tends to 2 to the right. Okay, x of f of x, this is equals to x minus 2 over x minus 2. Because to the right, I mean the limit x tends to 2 to the right, and this is equals to, this f of x will now be, because we are talking about limit to the right of this function, and to the right, this is just x minus 2 over x minus 2. So x minus 2 over x minus 2, this is equals to just 1. So we have limit x tends to 2 to the right of 2. This is equals to of f of x is equal to 1, because 1 is the limit. Directly after the cancellation, we have seen that the limit is equal to 1. So what are we saying? What we have now is that the limit does not exist. So we conclude, therefore, that limit x tends to 2 to the right, to the left of f of x is not equals to the limit to the right of 2 of f of x, because minus 1 is not the same thing as 1. And therefore, the limit of f of x as x tends to 2 does not exist. Does not exist. So we have another example. Let me see. Okay, maybe this is example 3. Let f of x be equal to SGN of x, That is the sine function of x, and that is equal to minus 1 if x is less than 0. It is equals to 1 if x is greater than 0. So we are asked to find limit f of x to the left of 0. So limit f of x at x equal to 0 is enough. We don't have to find. We know that the solution will entail the left and the right. Now, solution. To find limit f of x, limit of f of x as x tends to 0, we find the left-hand limit. So the left-hand limit says limit x tends to 0 to the left, 0 to the left of f of x, and this is equals to directly minus 1. One of the, this piecewise function is very important in determining, especially in physics, in determining a kind of motion or a force applied on a particle. So what this function is doing is that it assigns a kind of sign, negative or positive, on a function. Depends on what the function is. So if the function will take minus 1, so when x is less than 1, so it will be 1 if x is greater than 1. For all negative values, so the function will take minus 1. And for all positive values of x, so the function will take plus 1. That's positive 1. So it is known as the sine function. So already from the function is already defined. So the limit x tends to 0 to the right of f of x. So we consider this when x is greater than 0 for all values above 0 of f of x, and that is equal to 1. So it is clear that the limit f of x as x tends to 0 to the left is not equals to the limit of f of x as x tends to 0 to the right. And therefore, the limit f of x, x tends to 0, does not exist. Now, to close the class, we take the last example. Okay, not the last example, but second to the last example. So example 5. Let f of x be equal to 2x plus 1, okay, 7, and x plus 4, when, this is when, so if x is less than 3, this if x is equal to 3, and this if x is greater than, so x is greater than 3. So here, we don't have to consider when x is equal to 3. All we are after is when x is above 3 and when x is below 3. So meaning we are considering the left-hand limit and the right-hand limit for actually the limit to exist. So, solution. what is the left hand limit? So the left hand limit x tends to 3 of f of x. This is equal to, okay, so this is equal to this because we are talking about the left. So we have to take this value. So sorry, here, this value, we are talking about this, so we have to take this value. So it's equals to limit x tends to 3 on the left of 2x plus 1. And that is equals to what? 2 times 3 plus 1. And that is equal to 7. So also limit x tends to 3 to the left, to the right of f of x. This is equals to limit x tends to 3 to the right of, so we have to take x plus 4. And that is equals to what? 3 plus 4. And that is equal to 7. You see, what happened here is, despite the fact that the two functions, the defined functions here are different, but they have the same limit on the left and on the right. So you see that limit x tends to 3 on the left of f of x is equals to the limit of f of x, x tends to the right of 3, and that is equals to what? 7. So the limit exists and is 7. See, the two definitions of the functions are different, but the limit is the same. And so the limit exists. Now the last example. The last example, example 6 in this lecture. So we let f of x to be equal to the piecewise function x plus 2. That is if x is less than 1. It is 5 minus x if x is greater than or equal to 1. The question is, does the limit exist at x equal to 1, meaning when x naught is 1? Solution: to test whether the limit exists or not, we should find the left-hand limit. So we go directly, the limit of f of x as x tends to 1 to the left, this is equals to the limit x tends to the left of 1. So to the left of 1 is x plus 2. So we have x plus 2. And that is equal to, you just substitute when x is equal to 1. So you have 1 plus 2, and that is equals to 3. Okay, so the limit x tends to the right of 1 of f of x, this is equals to, so we consider this value now. So we are taking here because for x above 1. So x, when x is above 1, so it is equal to the limit x tends to 1 on the right of 1. So this is 5 minus x. Be careful. For the left-hand limit, we check when x is less than x naught. For the right-hand limit, you take the value, the definition of the function when x is above x naught, which is in this case 1. So this is equal to. So if here is 1, so you have 5 minus 1 and is equal to 4. So you see here that the limit x tends to 1 to the left of f of x is not equal to the limit x tends to 1 to the right of x equal to 1. And so the limit does not exist. Therefore, we conclude that limit of this function f of x, x tends to 1, does not exist. All right, thank you for your time. Till we meet in the next video.